Okay, so welcome back to this next video in which we are discussing cholera and pertussis toxin. Okay, so we've discussed G protein coupled receptors, we've discussed the G protein cycle. What we now need to discuss is the great diversity of heterotrimeric G proteins. So basically, what would be beautifully simple is if there was just one alpha subunit, just one beta subunit, and just one gamma subunit, and that was the one and only heterotrimeric G protein. But it is not that simple, unfortunately. There are a huge number of different alpha subunits, there are a huge number of different beta subunits, and there are a huge number of different gamma subunits. And this is the bit that's a bit of a headache, basically, but it's important for us to understand the function of pertussis toxin and cholera toxin. Okay, so let's now talk about the alpha subunits. Okay, so basically there are 16 different genes for alpha subunits, and when I say there are 16 different genes, I am not talking about homologous chromosomes here. I am talking about if you take one copy of each of the homologous chromosomes, I know we have two copies, but if you just take one copy of each of them, then on those, on that set of 22 or 23 chromosomes, if you're going to include the sex chromosomes, you will find 16 genes for alpha subunits of heterotrimeric G proteins. Okay, so you then get 21 different known subunits. There are 21 different known subunits for the alpha subunit of a heterotrimeric G protein. Now you might be looking at that saying, wait a second, there's something wrong there. How can we have 16 genes and then 21 different subunits? Well, basically, it's because some of these genes will actually produce more than one different type of protein. And you might say, well, how can they do that? Well, it's because of variations in the way that the mRNA will be spliced to produce a piece of mature mRNA. So let me just remind you of the central dogma of biology. Okay, so if we start off with our gene here, so let's say this is a gene for an alpha subunit of a heterotrimeric G protein, then what you will have is two strands of DNA which are complementary to one another. Now, when RNA polymerase II is actually going to work its way along the DNA and produce a piece of mRNA, it's going to produce that piece of mRNA that's complementary to one of the two strands of the DNA, not both. It only needs one of them, actually, to produce the piece of mRNA. The strand that it uses to produce the piece of mRNA is what's known as the coding strand. So let me colour this in purple here. So this piece is known as the, well, we'll let this piece represent the coding strand, so the strand of the DNA that's actually going to be used in the transcription process. The other piece, the complementary piece that is here in green, this is the non-coding strand, okay? So this is the non-coding strand. So what will happen, basically, in transcription of the gene for the alpha subunit, basically you will open the DNA, and then RNA polymerase II will work its way along this coding strand, producing a piece of mRNA that is complementary to that coding strand, okay? And let me colour this in turquoise. So this piece in turquoise is a piece of mRNA that is complementary to the coding strand. This piece of mRNA is what is known as the pre-mRNA. This is not the piece of mRNA you will actually put through a ribosome. If you put this through a ribosome, you will get a nonsense protein. And the reason is that there are portions of this mRNA, this pre-mRNA, which is the primary transcript, if you like, that should not be translated, okay? So, there are certain portions which should be translated. So, for instance, this bit might be necessary to actually be translated. This portion might need to be translated. This portion might also need to be translated. The portions that actually should be translated to produce a functional protein, so this piece, and this piece, these are known as the exons, okay? These are the portions that you actually should use to translate into a functional protein. The portions in between, so this portion, and these portions that I've left out on the ends, these are known as the introns, or the junk portions, okay? So these are the portions that you do not use in the actual translation. So what's going to follow is a process that is called splicing, okay, which is basically the process whereby the exons are going to be, the introns are going to be cut out, and the exons will then be rejoined together, okay, to produce a piece of mature mRNA, which will be shorter than the original pre-mRNA, but now won't have the junk pieces in, and therefore will actually code for something worth having. Okay, so this is the mature mRNA here. Right, so basically there are different ways that you can splice the pre-mRNA to produce a piece of mature mRNA. So for instance, there are an extreme example, it's not always this extreme. Some mRNAs will have exons that are actually optional, so they'll have an exon that you can either include in your mature mRNA, or you don't have to include it, you can remove it, completely splice it out as though it was an intron. And if you include it, you'll get a bit of a longer polypeptide than if you don't include it, but effectively both of the two polypeptides that you can produce then from those two scenarios, they will both function, but they might have slightly different properties, okay? And these two different proteins that you would then end up with, those will be called the two different splice variants of the gene. So basically, from a single gene, you can actually get many different pieces of mature mRNA in some cases. And these mature mRNAs, which all have slightly different structures, will then lead to different proteins. And these different proteins are then called the different splice variants of the gene. So when different proteins come from the same gene because you can splice up the pre-mRNA in different ways, those different proteins are called splice variants, okay? The different splice variants of the gene. Okay, right. So, basically, some of these genes can produce multiple different splice variants, okay? And that is why from 16 genes, you can actually produce 21 different alpha subunits, because some of the genes for these alpha subunits will then have multiple splice variants, and that's how 16 can lead to 21, basically. Okay, so let's now look at the 16 different genes for alpha subunits. Okay, so they are classified into families, okay, to help us get some sort of, to help us cope with the sheer number of them. Okay, so we're going to look at the genes rather than the subunits, because the notation for the different splice variants is just a nightmare, basically. And also, the different splice variants of the same gene, as far as we've been able to tell so far, they pretty much do the same thing. Okay, so we're not going to dwell on the different splice variants. We're going to look at the 16 different genes. So the genes are classified into 4 families. The first family is the G alpha S family, okay? And this contains 2 members, okay? So what are the members of this family? Well, basically there is the gene itself, which is G alpha S, and then there is another member. There's also G alpha olf. Now, G alpha olf does pretty much an identical thing to the G alpha S alpha subunit, okay? It's just, it appears to be the one that is used as a replacement to G alpha S in certain tissues, basically. Specifically, in the olfactory epithelium, you can find G alpha olf expressed in much higher levels than G alpha S, but it effectively performs the same role as G alpha S. It's a replacement, basically, in certain places. Now, G alpha S is a gene that has a huge number of different splice variants, and they've all got silly names, okay? But they seem to all do pretty much the same thing, so we won't dwell on that. G alpha olf, as far as we know, only has 1 splice variant, so it only makes 1 protein. Okay, so the next family is a much bigger family. This is the G alpha I/0 family of alpha subunits of heterotrimeric G proteins. So firstly, this contains 3 members which are all G alpha I's, okay? And these are not different splice variants, these are different genes, okay? So if you thought there was only 1 G alpha I subunit, you were wrong. There are actually 3 different G alpha I subunits. There's G alpha I1, there is G alpha I2, and there is G alpha I3. And I want to stress again, these are not different splice variants of one gene. You have 3 separate genes making these 3 separate alpha subunits. Yes, they perform pretty much the same thing, but they are 3 different proteins produced by 3 different genes. Okay, then you also have the transducin alpha subunits. Okay, so you have G alpha T1 and G alpha T2. Now, basically, in the photoreceptors in the eye, in the rod cells and the cone cells, basically the photoreceptor, the receptor which responds to light, is the rhodopsin photoreceptor, which we've mentioned earlier. It's the one after which that massive great family is named. Okay, and basically, when it is activated by light, it interacts with a heterotrimeric G protein, just like all other G protein coupled receptors. Now, the heterotrimeric G protein has a special name. It's called transducin, and basically, of course, these heterotrimeric G proteins have an alpha subunit. Okay, so this G alpha T1 is the alpha subunit of transducin in rod cells. So this is rod transducin, basically. It's the alpha subunit of rod transducin. G alpha T2 is then the alpha subunit of the transducin heterotrimeric G protein in cone cells. So this is cone transducin. Okay. Whoops, missed off the S. Let me just cross that out. Transducin. Right, okay, so that's where those two are used. Now, the family doesn't end there. It's a big, big family. And you also have a alpha subunit called the G alpha O, which is obviously one of the ones that this whole family is named after. Okay, that kind of does a very similar thing to the G alpha I's. You also have G alpha Z. Again, it has a similar function to the G alpha I's. Then you have another one called G alpha Gust, okay, which is involved in transduction of the taste signals in taste receptor cells. Okay, right. So those are the 8 genes within this G alpha I/0 family. Now, I do just want to discuss the different splice variants of G alpha O, because if you read the literature, you will encounter the 2 different splice variants of G alpha O, and I don't want you to believe that they are 2 separate genes. Okay, so basically there are 2 different splice variants of G alpha O, and they are G alpha OA, and then there's also G alpha OB. So those are splice variants, not separate genes. There's only one G alpha O gene. Okay, next up. The next family is the G alpha Q/11 family of alpha subunits of heterotrimeric G proteins. Now, the most famous member of this family is the G alpha Q alpha subunit of a heterotrimeric G protein. But it also contains G alpha 11, the other one after which the whole family is named. Then G alpha 14 is another member. And then finally, the final member has a bit of a more complicated name. It's G alpha 15/16. Okay, but do not think that this is 2 proteins, it's 1 protein. So let me tell you the story behind how it came to become known as G alpha 15/16. So basically, people doing research on mice found a new alpha subunit of a heterotrimeric G protein, and they called it G alpha 15. People doing research in humans found a new alpha subunit of heterotrimeric G proteins, and they called it G alpha 16. Okay, later it transpired that this G alpha 16 that we have found in humans was actually the same thing as they had found in mice years before. Okay, so there is now a movement to have both of them renamed G alpha 15/16. However, it's still prevalent to hear G alpha 15/16 called G alpha 16 if you're working in humans, and G alpha 15 if you're working in mice, so be aware of that. Okay, now, the final family, I think I could, if I'm actually now, I'll squash it in up here, okay, because it only contains 2 members. So the final family is the G alpha 12/13 family of alpha subunits of heterotrimeric G proteins. And this contains the G alpha 12 alpha subunit, and then also the G alpha 13 alpha subunit, okay? And that now concludes our discussion of the 16 different genes of alpha subunits of heterotrimeric G proteins. I'm sure your life has been revolutionized. Right, so let's count them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 6, oh no, what have we done? No, that shouldn't have been counted, that was the name. Okay, so there are 4 here, that takes us up to 16. Right, so those are the 16 different genes for alpha subunits of heterotrimeric G proteins. Okay, so there are 16 different genes, and then there are 21 different alpha subunits that are known, and it's likely that that number will go up as more and more research is done. So the message is that there are a huge number of different alpha subunits that you can put in this slot. When you're building a heterotrimeric G protein, you have a huge number of alpha subunits that you can choose from. And the importance of this is that certain G protein coupled receptors will only interact with certain alpha subunits, okay? So when they were going through the activation here, and the alpha subunit of the heterotrimeric G protein bound to the activated intracellular aspect of this ligand-bound G protein coupled receptor, the only certain alpha subunits will actually be able to bind with any decent affinity, basically. Okay, so G protein coupled receptors are coupled to certain G proteins, basically, and the G proteins that they're coupled to have to have certain alpha subunits. Okay, right. Now, the diversity doesn't end there. I'm going to take it further. We're going to discuss the diversity in the beta and the gamma subunits. Now, this is less important, it has to be said. The diversity in the alpha subunits, if you are going to learn some names, these are the ones to learn. However, the beta and the gamma subunits have a very simple naming system, so you might as well learn it just for completion. Although the functional significance of the different beta and gamma subunits is not understood at all. Okay, at the moment we're blissfully believing that it doesn't have any significance at all, but of course the reality is it's going to probably have huge significance in the future. Okay, different beta gamma subunits will probably activate different things. Okay, so let's now talk about the known different beta and gamma subunits then. Okay, right, so there are basically 5 different genes for beta subunits. Okay, so it's slightly simpler than the 16 we have for alpha subunits, and then there are 6 different subunits, but now we are armed to understand this bizarre phenomenon. Okay, we know what's happened here. One of those genes has had 2 different splice variants, and that is how you've gone from 5 genes to having 6 different subunits, and that's perfectly correct. Okay, so we'll start with the naming of the 5 genes, but I think I can handle the splice variants in this case, so we will discuss the splice variants as well. Okay, so the 5 different genes are beta 1, beta 2, beta 3, beta 4, and beta 5, so they're beautifully named, nice and sensible naming system. Okay, and basically it is beta 5 that produces 2 different separate known proteins. Okay, so beta 5 is the one that has 2 splice variants. So it produces the 2 beta subunits, beta 5-5, and then also beta 5L. Okay, the others, as of yet, only produce 1 known beta subunit. So the beta 1 gene produces the beta 1 subunit, the beta 2 gene produces the beta 2 subunit, the beta 3 gene produces the beta 3 subunit, the beta 4 gene produces the beta 4 subunit, to give us overall 6 different beta subunits. Okay, there we go, that's beta. Now on to gamma, and gamma's beautiful. Okay, gamma has 12 different genes, and thank God, 12 different subunits, so we don't have to worry about any splice variants of the genes, at least not yet, okay? So potentially in the future, we might find different splice variants of the different genes, but at the moment they aren't known. Okay, so we have 12 genes and they are beautifully named with one little blip in the naming. Okay, so the 12 genes are called gamma 1, gamma 2, gamma 3, gamma 4, and of course these code for the gamma 1 subunit, the gamma 2 subunit, the gamma 3 subunit, the gamma 4 subunit. So let's continue on, gamma 5, and then here's the blip. There is no gamma 6. It just goes straight on to gamma 7, and then there's no further blips. So it's gamma 8, gamma 9, gamma 10, and then we go on gamma 11, gamma 12, and you'd think maybe we'd have to stop there, but of course no, because we missed one out, so we're going to have to go on one further to gamma 13. So those are the 12 different gamma subunits, basically. Okay, so that now gives us a huge amount of diversity in the heterotrimeric G proteins that we can build. We have a huge number of different alpha subunits, we have a huge number of different beta subunits, we have a huge number of different gamma subunits. So in principle, if you wanted to name a heterotrimeric G protein, you would have to tell me the alpha subunit, the beta subunit, and the gamma subunit. So for instance, here's an example. G alpha I1 tells us that the alpha subunit is I1, then we'll have beta 1, and then also gamma 1. Okay, so you have the alpha I1 alpha subunit, the beta 1 beta subunit, and the gamma 1 gamma subunit. Okay, so that is a beautifully named heterotrimeric G protein. People hardly ever do this, okay? They will very, very rarely ever tell you the exact heterotrimeric G protein you are dealing with, generally because it's not known, okay? Certainly you don't know what the beta and the gamma subunits are most of the time, okay? So generally people never tell you what beta and gamma subunits we're working with because that's just not known. As far as we can see at the moment, it doesn't matter, it could be any of them, okay? And even then, people very rarely tell you the exact alpha subunit they're working with. Generally, people would call this a GI heterotrimeric G protein. So they tell you it was one of the, they tell you that it had one of the three G alpha I subunits as the alpha subunit. So people name the heterotrimeric G proteins by their alpha subunit, but rarely do they actually even tell you the exact alpha subunit, because even that isn't known. All they can say is it's one of the I's, basically, at this point. Okay? Sometimes people will actually even take it further than that. They will, well, further backwards than that. They will just name the heterotrimeric G protein by which family the alpha subunit is in. So they might just call this a G alpha I/0 to tell you that it's got an alpha subunit which is within the G alpha I0 family of alpha subunits for heterotrimeric G proteins. Okay, so that now concludes our discussion of the diversity of heterotrimeric G proteins. In the next video, what we'll finally turn our attention to is cholera toxin.